G'day, Richard Walding here from Brisbane, Australia. I'm just going to run through some experiments on Slinkys, using a Slinky as a solenoid and measuring the magnetic field strength using a smartphone, using the magnetometer in the smartphone. Okay, this is a presentation I'm doing for the University of Queensland for a conference in conjunction with the Science Teachers Association. It's also a presentation I'm doing down at Griffith University down the Gold Coast south of Brisbane. Okay, I've headed it solenoids and smartphones. Now, this is tied to the Queensland physics syllabus, the Year 12 physics syllabus. So let's have a look at some of the things we're going to try and achieve. The first thing is to have a look at what we're trying to achieve in terms of the syllabus. Now it says one of the things students should be able to do is to determine the magnitude and direction of a magnetic field, amongst other places, inside a solenoid, and then be able to do some problem solving on it. Okay, what I'd like to do is have a look at some of the ways that we've done it already, and the first one is this one. Okay, let me just run through some of this. This is a solenoid experiment where I've used these little bobbins off a sewing machine. They're little clear plastic bobbins, and I've just wound some wire around it, copper wire, and you can see on the screen I've done 400 turns, but this one's 300 I think, and then there's others of various sizes. That's 100 turns. Okay, I just used an electric drill and a digital stroboscope to do that. Okay, so that's one way we can do it, and that's worked really well. Another way is to use a proper magnetometer. Okay, so this is a Kinetec magnetometer. Okay, so that's a commercial one. It's used in industry, highly accurate. And these are about $1,000 new. And there's the probe that goes with it. So that's a little Hall effect probe on the end. You might be able to see just on the end, there's a little spot on the end where the Hall effect probe. So what you can do is measure the field inside these little bobbins using that probe. Now that hasn't worked that well, but it's just an interesting way of doing it. Another way is to use a Slinky. Okay, so I've got the Slinky here, and you can actually measure the magnetic field strength inside the Slinky, right, like inside there, right in the middle. Now, not at the end. I don't want to measure it at the end. We want to measure it actually in the middle, because the formula works for the centre of a solenoid, well, a Slinky in this case, and you can use your Hall effect probe inside there, right, or you could put it through the side to get it in the middle. You can see it in the middle there. Okay, so that works fairly well. Now, I've actually done that. And you can see the address is on the screen now. I've put that on YouTube, the results of that. And the other way we can do it is using a smartphone, okay, like on the screen. So you can use your phone, in this case it's an iPhone, using a magnetometer app, and that's called Magnetometer, this particular one, and it gives a reading. I don't know if you can see it, but there's a reading there of about 69 microtesla. Okay, so that's another way of doing it. Now, in schools, you've probably got these sorts of solenoids. Now, they're fixed. There's a certain number of turns. It might be 250 turns of annealed copper wire. Okay, it's got a coating on the outside, like a varnish coating, and you can see it's a hollow tube. Okay, so the length and number of turns are fixed. So you can't do a lot of experiments with number of turns and length on that sort of solenoid. Okay, let's now have a look at the mandatory prac for senior physics. Now, this is in Queensland anyway. One of the pracs you have to be, or the students do all over Queensland, is, as I've got it on the screen there, conduct an experiment to investigate the strength of a magnet at various distances. Now, you can do that, and all students have to do this. You can do that a number of ways. Now, the strength, or the magnet it could be a permanent magnet or it could be an electromagnet. So you could set up an electromagnet and measure the strength at different distances, 10, 20, 30, 40, 50 centimetres away, or you could use a permanent magnet and do it the same way. Now you could measure it using an iPhone or like a magnetometer in a smartphone, or a magnetometer that often comes with the data collecting apparatus you might have at school, or you can hire or get hold of a commercial magnetometer. Now they range in price from about $150 up to a couple of $1,000. Okay, and actually for the strength you can either use the magnetometer or you could use the force that a magnet puts on another magnet and measure the force, the change in force as the magnets are moved closer and further away. That also works. Okay, now for the experiment you're going to develop out of that, you need a rationale. Now in the syllabus it gives the formula B equals mu 0, and well, it doesn't actually say N on L, it says small n, which implies the number of turns per metre, and I've changed that to N on L times I, the current. That implies that the magnetic field strength B changes with N, I and L. So you could measure any of those three variables and make a good prac. Now I'm only going to concentrate on N and L, okay, because that's the most interesting one for me with a solenoid, with a slinky. So my first experiment is going to be, how does the length of a solenoid affect the magnetic field strength if you keep the current and number of turns constant? So you're going to have a look at B and L. Okay, that's the first experiment. The second experiment is going to be between the number of turns, N, and B. Okay, so they're the two experiments I'm going to use. Now, in the syllabus, like I said, there's one formula, and that's it there. B equals mu 0 n, little n, times I. Now that little n stands for turns per metre. The other bit of information is the magnetic constant, mu 0, that's it here. It's equal to 4 pi by 10 to the negative 7 Tesla per amp metre. Now if you multiply that 4 pi out, it comes to be 1.26 by 10 to the negative 7 Tesla per amp metre. Okay, so, but what is not in the syllabus, as I said, is converting that n, the number of turns per metre, into a formula, so N on L. So we can expand that and make the formula we're going to work with that. Now the first experiment is the relationship between B and L, and you can see if you keep the other three constant, B is proportional to 1 on L. So what it should look like is an inverse relationship. So B as a function of L is just that inverse relationship. Okay, so that's what we're going to aim for with our experiment. Okay, so about setting up the circuit now, you've got to keep the current constant, and so I've got the circuit here. So the only way one way to keep the current constant is to use a potentiometer. Now you're using that as a voltage divider. So let's say you've got it set at 12 volts or something, it doesn't matter, a couple of volts anyway. To get the current you want going through the slinky, you have to adjust the voltage. Now if you've only got a power supply that goes in 2 volt increments, that's a bit tricky. So you'd have to put in a potentiometer like this, and so B will be 0 volts, so that's the negative of the terminal. B's at 0, so the slinky down here is at 0, and A, this point A, will be at whatever you've got this set at, let's say 12 volts, and then by moving this slider back and forth you can adjust the voltage here, anything from 12 volts down to whatever you want to get down to, so maybe 3 volts or something. You just slide that down. The further you slide it, the lower the voltage. Okay, and so if you want to have 0.2 of an amp, or if you want to have 2 amps on the ammeter, you just adjust that till you get 2, and it should stay constant for the whole experiment. If it doesn't, you just tweak this a little bit to keep it constant at whatever voltage you're using as the control. Okay, now 10 turns of a Slinky. The first experiment, let's look at keeping it at 10 turns. That's about 0.3 of an ohm. Okay, so 50 turns, that'll be what you might want to go up to. At say 2 amps, needs about 3 volts. So the Slinky works well. You only need about 3 volts. So an ordinary laboratory power supply will easily do that, and it gives you a current which is about 2 amps. Now you don't want a current that's too high, because most of the power supplies are current limited, so at 5 amps they might just switch off, so just to protect from overheating and so on. So 10 to 50 turns of a Slinky at about 3 volts gives you a reasonable sorts of readings. It won't get too hot, and you'll be able to measure it nicely on the ammeter. Okay, so here's the setup I've used to try this out. Now, the potentiometer I'm using here is one I bought from JCar. They're about $17 or $18. They're 5 ohm, 15 watts. So they'll take 15 watts. So if you multiply V by I, it can handle up to about 15 watts. The trouble is, at 15 watts, they're really hot and they start to smoke. You want to get them probably down to between 5 and 10 amps, 5 and 10 watts at the most. So they're only little ones, but they work all right, as long as your voltages and currents aren't too high. Okay, and there's my Slinky with the 10 turns. And I'm using a meter here. This is the ammeter. You can see I've got it on A, ammeter for DC direct current, and it's reading 2, I think it says 2 amps, 2.011 amps. Okay, now over in this other side of the screen, you can see the ordinary old power supply. Now these are the ones I was telling you about that are the standard laboratory power supplies. They go up in 2 volt increments. They don't tend to hold their voltage constant throughout the prac, because what happens is as the load on them changes, the voltage can either rise or fall. There's no really set way of knowing whether the voltage will rise or fall. It's a funny sort of a device, and you just can't predict. So you've got to use a potentiometer that allows you to keep this constant at whatever you want. In this case, it's 2 amps. Okay, these are 100 watt potentiometers, so they can take a lot more current and higher voltage across them. They're about $120. You buy those from science supplies stores. Okay, a more recent one is the circular one. I'll just show you that. Now these are the ones currently on sale. They're made by IEC in Australia, and they're 100 watt, and they work really well. Teachers are quite happy with those. They work nicely. They can take the voltage and current, and they're good as a potential divider. Okay, but if you've got the money, and I know a lot of schools have got these, you can buy a regulated power supply. Now I got this from JCar, about nearly $200. But what it allows you to do is to either set the voltage or set the current, whatever you want. Now you can see the red light here says constant current. So I've adjusted this and clicked on the current knob so that we get a current of 2.000 amps. Okay, now that no matter what load you put on it, providing you got enough voltage across it, no matter what load you put on, it'll stay at 2.000. It adjusts itself automatically, and you don't have to really worry about how the current will change during the prac. So these are ideal for $200. They're not that much, about the same price as the IEC ones really. So a lot of schools have these, or this type, maybe not this brand, but I'm pretty happy with that. That's a JCar. Okay, like I said, you set it to the current you want. Okay, now you could also change it to a constant voltage and set it at say 8 volts. Now, for instance, I use that when I'm doing electrochemistry experiments. You want to do some electrolysis and you want to have the voltage constant at, say, 8 volts. You just switch this to constant voltage. You set it at 8 volts. And the current rises and falls depending on the experiment. Okay, let's have a look at the setup. Now, this is just a tabletop. Here's a Slinky, and I've got a mobile phone stuck in there. Now, I know the magnetometer is down in this corner, this top left corner, if you were holding the phone the normal way. Okay, I've got it set at 2 amps, and you mightn't be able to read it, but that says 106, and the unit is microtesla. Okay, the question is, where is the magnetometer? So let's have a look. I just noted these points I just went through. Okay. Oh, by the way, a lot of these digital voltmeters or multimeters, they appear to work, and teachers or students often say, I can't get them to work on current. They're not giving a current reading. They're giving voltage and resistance. What happens is there's a fuse on the current input, and so you can blow the fuse. Students might hook it up to a power source that's too high and too high current. It'll blow the fuse, but it allows the voltmeter and the ohm meter to still work, and it's very puzzling for the science technicians in the schools to work out what's wrong. They have to take them apart and change the fuses. Okay, now this is the magnet meter I was telling you about. This is from an iPhone, and in this case it's reading 118 microtesla. Okay, now the program, there's lots of programs around you can use. Another one is from Physics Toolbox. This gives you readings in 3 dimensions, X, Y and Z, and a combined one. Okay, it goes with time. So as time changes, as the time goes by, you can get readings on that. Probably a little bit harder to read. You'd have to decide whether you're looking at the X, Y or Z axis. Okay, I'm quite happy with this one, but there's lots like that. The question is, whereabouts is the magnetometer? Look, what I did for this is I just ran a little magnet over the corner. Now I know it's up in that corner somewhere, so this is what I did. Just got a little magnet with a pair of tweezers, and you'll notice the reading 6,000. Okay, it gets up to about 6.5. Nearly 7, oh there we go, 7,900, just where I've got that magnet. Okay, now this is just a Samsung, this is a quick one. You can see it's going to be up there, the reading 192, but that gets up to about 8,000 I think. Okay, 8,000, so somewhere up in the same corner. Okay, so back here you could mark on the phone where it is, and I'll just put a little dot there. Okay, so you know it's about 1 centimetre in from the top left, 1 centimetre each way. Now it doesn't really matter if you don't get it exact, as long as you keep that point wherever you decide is the magnetometer and you take your measurements from it, about 1 centimetre in both ways, and the same is pretty true of Android phones. Okay, let's have a look at some results. Now I've got a lot of photos here. The reason I've done it is a lot of teachers have said to me they can't do these experiments. The student's been away and they've been at some conference, or they've been away for some sporting team, or they're sick, or the equipment's broken or whatever, and they can't do these experiments. So what I've done is taken a photo, and students can just write down the results and use it as raw data for their own experiment if they get stuck. I'll go through that, how you can do that. So look, I've measured the background. This is with the no current, so it's 0 current, and you can see I'm using 10 turns. So if you count those, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's a couple missing off the off the screen. Now the first reading, I'm calling it trial number 1, 10 turns, 2 amps, and a length of 10 centimetres. So it's 10 centimetres from where I got the alligator clip to the end where I've got the other yellow alligator clip. So that's 10 centimetres, and I've got 10 turns, and I'm running 2 amps through it. And you mightn't be able to read off the phone, but the magnetometer reading says 218 microtesla. So I wrote that down, and students could write that down. So then I tried duplicates. So, this is 15 centimetres now. So I've expanded the coil to 15. I've still got 10 turns, and I've still got the same current at 2 amps, but I've expanded the length of it, and that's the beauty of the Slinky. And you can see I've only got 164 microtesla. Then I expand it to 20. I've got 128 microtesla, and I keep going. 25 centimetres, 107, 30 centimetres, 93, and then 35 centimetres, it's a bit off the screen, but you get the idea. 83, you can read that pretty clearly on the phone there, 83 microteslas, and 40 centimetres, 76 microteslas. Now, I've then done trials 2 and 3. Now, this is basically to show you that I've actually collected raw data. This is not just some made-up data, so it'll have any uncertainty built into it, and it's good for error analysis. So students can copy this down and do it. So I'm doing trials 2 and trial 3. This is for both 10 centimetres. You can see one's giving 221 microtesla when I repeated that. I didn't just leave it in the same spot and measure it again. I actually did the whole experiment and then went back and did it a third time. I think that's the best way to get the uncertainty meaning something. If you just write down the reading twice, you're not really doing two independent trials. Anyway, that's 212 microtesla here. And so we continue on at 15 centimetres. You can see there's a little bit of difference in the readings, 158 and 161. So a little bit of uncertainty there. 20 centimetres, look, they're both 125. Now I haven't rigged that, this is genuine. And, okay, 25 centimetres, 105, 106, and 92 and 93 microteslas, and 83 and 84, and 77 and 77. Okay, so that's worked pretty well. Now, I've put all the results here in a table, just so you can see how we go. So I've got the various lengths of the solenoid and the magnetic field. Now there's my 3 trials, and I've got all those results, and I've worked out an average, and there's the uncertainty. So it's the maximum minus minimum divided by 2. So it'd be 221, which is the maximum, minus the minimum, which gives a reading of, that's a difference of 9, divided by 2, it's 4.5. And then I've expressed that as a percent of the average. Okay, so I've done that for each one, so that's good for when I'm doing error bars. Now before we plot that, let's have a look at the data. What often happens with data tests, well, you'll get some, it could be in an external exam or somewhere, there'll be a table of data, and might even be a multi-choice question. It'll say, it mightn't actually give you all the trials, it might have the change in X and the change in Y, and it'll say, what sort of relationship is there between the X and the Y? And it might give you multi-choice. It might say, is Y proportional to 1 on X? It could be A, B, C, and D. Now you'd look at that and say, is it, students would look at that and say, is Y proportional to 1 on X? As Y increases from point 1 to point 4, the average is going down. So it looks like it's an inverse relationship of some sort. Okay, so it's inverse. You could rule out this Y proportional to X. So it's inverse. Now could it be 1 on X? In other words, Y proportional to X to the minus 1? Or is it inverse squared or inverse cubed or whatever? Now when I've got, I tell my students to do this, we have a look at what happens when you double the X. Now in the length here is doubled from point 1 to point 2. Okay, so it's doubled. If it was straight inverse, the average would halve. So as you double this one, for an ordinary inverse relationship, this would halve. So 217 would have to go down to 108 or something like that. Now it's not going down that far. Okay, so the question is, it's not exactly 1 on x. Is it 1 on x to a higher power? Instead of 1, it could be negative, or it could be 2, or is it less than 1? Okay, so the simplest way is to see, is it inverse squared? So as you double this, if it was inverse squared, this would be a quarter. Okay, a double inverse squared would be a quarter. So a quarter of 217 is about, what, 50 something, and it's 126, so that's worse. So it's certainly not inverse squared. So it's probably something less than 0.1. Now, you'd never be able to do that without plotting it, and it'd be a bit hard to try and do a multi-choice and work out the exact value, but at least it'd be less than 1. So it might be y is proportional to x to the negative 0.6 or 0.8 or something. Okay, so let's move on and we'll plot it. And I've plotted the length of 10 turns along the bottom in meters. So I've changed from centimeters to meters to get it into SI units. And the magnetic field B in microtesla along the y-axis. And you can see this lovely curve. It's an inverse of some sort. Now, I've asked Excel to do a trend line and give me the formula for the trend line, and it's shown me that it's a power trend, a power relationship, and it's minus 0.7. Okay, so we were testing out whether it was minus 1 or minus 2 before, and we decided it was less than minus 1, and I said maybe 0.6 or 0.8, but it's actually 0.7. Okay, so that's our relationship. So students could report on that. And the R squared value, that's the goodness of fit for the data with the equation. So that equation for the trend line captures basically the data extremely well. So anything over, I tell my students, anything over about 0.98, and you can make some comments about the quality of the fit between the graph or your own data and the equation. So that's looking pretty good. Now the next thing physics students would do is to try and linearize that. So what they'd plot along the bottom is 1 on x, or x to 1 on x to the power of 0.7. We could just try 1 on x, or we could try a number of things here. So in this one I've just plotted 1 on L, so 1 on x. Now we know it's not exactly 1 on x, but it's giving a good inverse relationship. Look, this is a lovely line. It's the dots. Now I'll just go back one. The question is, how many data points should I take? I've used 3 and 4 is 7. So I've used 7 variations of the independent variable. Now sometimes people will say use a 5x3 model. Okay, so look, I'll go back to the original data here. Now I've used 7 variations on the length and 3 replicates. So I've used a 7x3. Now I knew this was going to be a curve, a non-linear relationship based on the formula. So it made sense to me to collect 7 points when it's non-linear. 5's all right for linear, but if you can and you've got the time, get a few more. But certainly do 3 replicates for each one. Then you can add the error bars, which I've done. Okay, so that's a nice linear relationship, and here's the relationship, the formula for the relationship, 0.998 as the R squared value. Okay, now there are error bars present. The only one you can really see is this one up here. The rest are tucked away behind the markers. Now you'll notice it intercepts the y-axis at about 30. Around about 30. Now that 30 microtesla, now that's the background. Okay, so if you remember when I had 0 current flowing through the solenoid, it was giving a reading of about 34 or 36 microtesla. Now what you could do is subtract that from all of the readings. I'll just go back to the data table here. Now what you could do is subtract 36, or whatever you measured the background to be, off each of these, and when you plotted it, this one would go through 0. Now it doesn't really matter, it's the gradient that you're interested in, not the intercept. But that's something students could talk about, why there's this appears to be a systematic error, but you can account for that by saying it's the background radiation. Okay, let's move on. I mentioned that it doesn't make any difference to the gradient. Now, the gradient is change in y over change in x, so it's b divided by 1 on L, which is the bottom one, and if you rearrange that you get the gradient's equal to BL. So we'll keep that in mind for later. Okay, now I've plotted knowing the exact values of B, of I and L, and number of turns, we get a graph shown by this orange line. And what you'll notice, it has a slightly different gradient. The intercept is around about the same. The intercept's 34 for the theoretical and 30 or so for the experimental. Okay, so you could comment on that. Now, you could express the error, which is the difference in gradients, and divide by the theoretical to get a percent error in terms of the gradient. That'll give you a nice set of results to talk about. Okay, for the analysis, let's have a look. Now, the question is, what are we trying to find? In this case, I've decided that what I'm going to do is to try and calculate, using my experiment, the value of mu0, the magnetic constant. Okay, and then I can compare it to the accepted value. So B equals mu0 n on I, which I told you is n on L for n. And you can rearrange that. So BL equals mu0 ni. Now BL I mentioned before is the gradient. So the gradient is B on 1 on L equals BL. So the gradient should be equal to mu0 ni. Okay, so mu0 for experimental value is the gradient divided by n times I. Now if I substitute in, the gradient is 18.94. You can see that off the blue line here, or the blue box, by 10 to the negative 6, because we're talking about microtesla, divided by 10, which is the number of turns, divided by 2 amps, 2.000 amps. Now 10, even though it looks like it's only got 1 or 2 significant figures, that's 10 turns. It's a 10.00 if you like, because we're not doing 11 turns or 9 turns, it's exactly 10. So I can just leave it, and it's understood to be a few significant figures extra. Okay, so mu works out to be 9.47 by 10 to the negative 7. Now I can compare that to the accepted value. The accepted value, straight out of the syllabus, I just cut and pasted this out of the syllabus, is 4 pi, and I told you before that's equal to that value there. So I'm comparing my experimental value to that number. So the absolute error, now I'm using EA as the symbol. The syllabus doesn't mention it, but in the Oxford text, in my Oxford test, I'm calling it EA, and that's fairly consistent around the world. It's equal to the accepted value of x, or whatever you're measuring, x, minus the observed value for the same quantity. And here I get the accepted value, which is this 1.26, minus, from the previous page, 9.47. But remember, that's by 10 to the negative 7. So it's actually 0.947 times 10 to the negative 6. Take it away, and we get that. So that's the absolute error. The next thing we'd like to do is to convert that to a percentage error. Now, in my Oxford text, I use E%, and that's fairly consistent around the world. So it's equal to the the absolute error divided by the accepted value for the quantity times 100. Now, in the syllabus, they define that using words rather than symbols, and so the students have this in this form. So percentage error is measured value minus true value over the true value. Okay, you end up with the same sort of thing. Okay, so let's substitute in, and the errors on the top, the accepted value underneath, and we get about 25% error. Now that seems high, but it's not so important that we get an experiment that gives really low error. The question is, how do we account for that? So what students are trying to do is to demonstrate their understanding, that they understand what's happening, even if their data collection is not the best. They're still working with raw data. They're still manipulating it. They're still analysing it and discussing it and so on. The fact that it's not closely aligned with the accepted value is really of no consequence. It gives them more to talk about, if anything, so that's okay. Okay, sources of error. Now, I've eliminated the background. We're not talking about that. But what else could be going on? Look, if you increase the experimental values B artificially by 33%, so you multiply everything by 1.33, if you like, you get this beautiful fit. Now, so there's zero error basically. The question is, what does multiplying everything by 1.33, the experimental values, do? Why does that work? Okay, I'm not quite sure, but obviously it's something to do with the magnetometer, whether it's reading in the right direction, whether it's reading the particular axis you're trying to measure, and whether, it couldn't be just random errors. It's something quite systematic there. So that'll be worth something commenting on and trying to evaluate. So that's a nice little experiment. Okay, so the error calculation reduces to zero if you multiply this artificially. It's just a way of wondering what's going on. Okay, now I've got another set of data. I did this experiment a few times. And this one I've used 3 amps rather than 2, and I've used 15 turns rather than 10. So I've collected data. Now I'm presenting that here for students who are away, or their experiment didn't work, or they've been sick, or they've been at some sporting event, or representing the school, or whatever's happened, on holidays even, or if the equipment's just failed, or they had trouble with it and they didn't realise it was wrong. So it could be useful if they're away. Now, this is still raw data. Just be careful you're not thinking, well, this is second-hand data because it's coming from me. It's still unprocessed. So the syllabus is not, or the marking guide is not so interested in how you collect the raw data. It's telling a story. It's your report tells a story about how you've collected the raw data or where you've got the raw data from and how you're manipulating it. The fact that you're getting it from another person, now this could be another group in the classroom, but long as you acknowledge that you got it from somewhere else and you didn't collect it yourself, that's fine. So just acknowledge the source in the report. Okay. Now the second research question is, how does the magnetic field strength inside the solenoid relate to the number of turns? Okay, so this is going to be a lot simpler because it should be a direct relationship. We're keeping current and length constant. So there's the formula again. So that implies B is proportional to N itself. So it's directly proportional. So it should look like that. Now the trouble is, with a smartphone, you can't zero them. Now a magnetometer that I showed you before, the Kinetec, you can actually push a button and it'll zero. It'll take away the background reading straight away. And so what you're getting is the actual addition to the magnetic field due to the solenoid. But using a smartphone, what we end up with is this. So we get a little bit of background. Now it doesn't affect the slope or the gradient. It just adds, 34 microtesla to the reading. Now you could subtract it, or you could still go ahead and plot it and just acknowledge that it's the background. Okay, so here's my experiment. Look, the background for this part was 36 microtesla. There's zero current going through it. And I'm using 0.3. I'm using a 30 centimetre length and 2 amps going through it. Okay, so I'm changing a number of turns. 5 turns, I'm getting 63 microtesla. And we keep going. 10 turns, 15 turns. You can see the more turns you're using, the greater the B value, the magnetic field strength inside the solenoid. 20 turns, 25 turns, it's getting bigger and bigger. Now I'm showing you these just so you can see that it's raw data, I haven't made it up, and students can use this as a practice plot, and or they could use it for their report. Okay, 30 turns, it's getting more. I think I stopped at 30, getting 240 microtesla. Okay, you can see it on the phone there. Okay, so we plot it and we get a lovely straight line, as you'd expect. Number of turns along the bottom, the field strength B up the side, and of course the intercept is around about 25 to 30, somewhere in there. So the trend line has an intercept of, look, here it is here, 25.2. The magnetometer was on the phone was saying about 34 or 5, and the gradient is written here 7.3. Okay, lovely high R squared value, meaning the line, the trend line basically cuts through all of the points, or nearly all of them. The error bars, there are error bars in there, but you can't see them. Okay, now you can plot the theoretical value, and you get that. You'll notice the slope is a bit different. Even the intercept's a bit different. So that's interesting, something to think about, and you can get some good marks doing the discussion about why there is a difference, what you could do to find out why there's a difference, or just trying to explain how your experiment has given you this difference and what the source of it might be. Okay, so the analysis of that final experiment, same formulas as before. The gradient is equal to B on N, which is equal to mu 0 I on L. Okay, so mu 0 is the gradient times L on I. So if we substitute the numbers in, there's the gradient I mentioned before, times L, it was a 30 centimetre or 0.3 of a metre slinky, and divided by the current of 2 amps, we get 1.1 by 10 to the negative 6 for my experimental value of mu. And if we do an error analysis, we take the 2 away and we get an absolute error, 1.57 by 10 to the negative 7. And then as a percent, you put it over the accepted value, and that's 12.5%. So that's less than the percentage we had for the other method. Now that doesn't matter, it's just a percent, it's just something to talk about. Okay, students can have this raw data. This is from a separate experiment I did, and you could either get them to plot this as a homework or a worksheet or something like that, and to comment on all of that, or they could use it as, like I said before, if they're away. It's still raw data, so it can be used in their student report, so long as you acknowledge it. That'd be nice, and I've put the background in there. Okay, look, just to show you how it compared with the previous one I did on YouTube. Now there's the YouTube link. You just have to look for something like Slinky and solenoid and magnetic field, and you'll see it. This is 2 amps, and I collected some data using this professional magnetometer. There's the graph I got. Now that gave me an error of 6%, much less than the iPhone. Okay, so something for us to talk about here. Not a student wouldn't talk about that because they wouldn't necessarily have access to any of this. Okay, so that's the end. If you go to that website there, you'll see the link to the YouTube videos. But I've also handed out to teachers doing this presentation a set of 3 questions on solenoids and about graphing. They're sort of typical of the data test questions, or even data analysis questions you could get on an external exam. If you didn't get a copy, there's the link to my website, and you can just download a set. It comes with a marking scheme and so on. So that's all for today, so thank you for that. Goodbye.